Hello students, welcome back. Previously we went through the concepts of equivalence relation, equivalence class and their properties, equivalence partition and quotient set. And also remember, the quotient set can have much smaller cardinality compared with the original set. Remember all those? Alright, let's go to an example, modular equivalence, which begins from the set of integers, and this corresponds to my capital X. And with respect to a certain positive number m, let's define an equivalence relation like this. A and B are congruent modulo m, or A and B are equivalent modulo m, if and only if m divides a minus b, or equivalently speaking, a minus b is divisible by m. This expression here, the final expression, this one is going to be the most useful in terms of proof. So a minus b is divisible by m. That means a certain integer, the quotient, times m. And this quotient has to be an integer, of course. Now, please note that we have an existential quantifier here. That means each time you use this, you have to bring in a new character. Q1, Q2, Q3, like that, or QRST, kind of like that. You cannot use the same Q thrice. If you have a universal quantifier, then you can use same epsilon all the time. For existential, no. Okay, let's go ahead. Let's prove that this is an equivalence relation. In other words, you have to prove the reflexivity, the symmetry, and then the transitivity. Again, remember this bold form. A and B are congruent modulo m means m divide a minus b. In other words, a minus b is divisible by m, or in other words, is certain integer times m. Okay, let's begin. First, let's prove the reflexivity. A is equivalent to a, so here b is equal to a, so a minus a is something times m. That's easy. That's 0 times m, isn't it? Yeah, integer times m, 0 times m. That's it. Q is m. There goes the proof. Now the symmetry. A is congruent to b, so like this. Then b is congruent to a, so we have to change b minus a. So that's divisible by m. In other words, that's what you want. A minus b is divisible by m, then b minus a is divisible by m. So if this integer is a certain q, then what is this integer? Negative q, of course. There goes the proof. Now the transitivity. In this case, we have two conditions, two congruences here, 1 and 2. And we have existential quantifier, so we need two characters, q and r, or q1 and q2, kind of like that. Here's a reminder. A minus b is divisible by m, so it's an integer, say q times m, and b minus c is divisible by m, so it's an integer, r times m. Then a minus c is divisible by m. We have to find certain integer here. In this example, r looks too much like a remainder. Let's change this into s. Okay, so how do you get this integer? Well, if I add them up, a minus b plus b minus c, then that's going to be a minus c. So you're going to get an easy expression like that. Here we go. Yeah, instead of q and s, I use q1 and q2 here. That's okay. So, and then we have addition. So factoring out m, we get q1 plus q2m, and q1 plus q2 is an integer. So yes, we have transitivity as well. Okay, now that we proved that this is an equivalent relation, we have equivalent classes and quotient sets. Let's define addition and multiplication into a quotient set through induced addition, induced from integer addition and integer multiplication. Are they well defined? That's the question. In other words, if I select different representatives, do I still get the same answer in the end? That's the key question, you see. We defined in terms of the integer arithmetic. So if I take different representative, we may get different pair of integers, and that may create different equivalent classes. In that case, everything will break down. This problem says that never happens. The final answer is the same. And of course, you have to do the same thing for multiplication as well. One step at a time. You have to prove that if these two classes are the same and these two classes are the same, then these two classes are the same. When do we have two identical equivalent classes? There you go. Two equivalent classes means the representatives are related. So representatives should be related according to congruence modulo m, or like this. So you have this one and that one. So you're going to get q1 and q2, kind of like that. Here we go. a1 minus a2 is qm, yes, that's related to this. And b1 minus b2 is sm, that's coming from there. So you see, we use this bolded part twice, but this is an existential quantifier, so we need two different characters, q and then next character s. And then we have to prove that the difference is divisible by m, something times m. How can you prove it? Doesn't look too bad, because here a1 minus a2 and then b1 minus b2, so it looks like I can simply add them up. Let's do that. So okay, that's qm, that's sm, and then simply add them up. What do you get? Rearrangement, a1 minus a2 plus b1 minus b2. The first is qm, second is sm, so then we get q plus s times m. Yes, we got an integer times m. That completes the proof. All good? Question? How about the second proof? We have to do something similar. Here we get qm, there you get sm, but instead of addition, we have to have multiplications. Here's the setup. Make sense? Okay. Exactly the same compared with addition versus multiplication, but this manipulation is not that trivial. Any idea? Want to stop the playback and try on your own? Here's a hint. Okay, that's qm, that's sm. And then, let's do this. Subtract and add the same thing, so that net addition is 0, so I didn't change anything. So it's the same as original, but by doing that, I can consider these two and the second two separately. Does it make sense? And what do we do next? First two, and second two separately, and from first two, B1 is common, factor out. From second two, A2 is common, so factor that out. As a matter of fact, when you're inserting this cross multiplication, A to B1, A to B1 like that, you're kind of expecting this. You could have done it as A1, B2 if you preferred, actually. Either way, it'll work out. This technique, cross multiply and insert minus plus so that adding nets 0, this technique is very, very common in analysis. In the proof of limit rules, derivative rules, some continuity, and so on. But here in algebra, it's not that common, but here in the end, we used it. So use that and then separate these two. And then B1 is common, A2 is common, and then A1 minus A2, yeah, you have QM, and then we have SM, and factor M out. So what do we have? Some integer times M, precisely as we wanted. So what's the conclusion? Multiplication is also well defined. Even if I get different representatives, eventually I end up with the same addition and same multiplication results. So the addition and multiplication induced by integer operation, integer addition and integer multiplication, stays valid in the quotient set. Now, if we identify what exactly does the quotient set look like, then all will be done, and it turns out that's the quotient set. We end up with a residue class. Dividing by m, so remainder can be either 0, 1, 2, 3, all the way up to m minus 1. And this thing is typically called residue class. For some reason, it is called residue class instead of remainder class. I think the reason is historical. And here's the proof. Let's apply the division algorithm. Any integer, you can divide by m, and we get a remainder which belongs to the set 0 to m minus 1, because if it exceeds or at least equal to m, then you can divide further and then reduce this remainder further down. And this applies for negative integers as well, because q can be negative. And then if I flip this r to the other side, what do you get? The right hand side is qm, so n, the original arbitrary integer, is congruent to a certain r, and that r comes from any one of these, 0 through m minus 1. So no matter what integer I start off with, it's equivalent to one of those, and there are m minus 1 of those. Therefore, we go to a conclusion like this. If I take any equivalent class that belongs to the quotient set, that equivalent class is equal to either 0 bar or 1 bar all the way up to m minus 1 bar. And the residue class is typically expressed as Zm. So, the conclusion. The addition and multiplication is well defined in this residue class. We can do all kind of addition and multiplication simply by the usual addition and multiplication, and then in the end you can take the residue or take the remainder. You can take the remainder in the middle as well, do whatever you wish to. We're going to do those kind of operations in a little bit more detail in section 2 of this notebook. But whether it is well defined or not, well, that one we completed here. Okay, that completes modular equivalence.